Welcome to Chapter 9 for Structural Geology and Mountain Building. Now, in structural geology, we analyze all the processes that go into changing the shape or deforming the Earth's crust. Now, this is important for several reasons, especially when we look at civil engineering factors. If civil engineers don't understand how rocks can be weakened, then if we are trying to build, say, a highway or a dam in an area like this that has some deformed rocks and they do not take that into account, it can cost lives, and it already has many times in the past. Now, when we talk about deformation, we're referring to any changes in the orientation or shape or size of the original rock body. Now, this typically occurs along plate boundaries, especially convergent plate boundaries. And all this deformation involves a lot of force. And so a force in physics is anything that would cause a stationary object to move or change the direction of movement for an object that is already in motion. Now, when we look at the deformation, again, deformation involves stress. Again, that's just force applied to a given area will cause that stress. But there are different types of stresses that can act on a body. What we call compressional stress is something that is shortening a body. So if we have a, sorry for my doodle there, but if we have a block of rock like that, and we're compressing it, we're pressing on it from the sides like that. Now, typically, if you're pressing in one direction, another direction will be experiencing extension. And so that's what we see here. So typically, we have extension going on at a right angle to where the compression is acting. Now, the third stress that we're looking at here is shear. Now, shear typically happens at an angle relative to the compression and the extension. And so we've drawn in the various angles like that. And so this angle here typically is about a 60-degree angle. Now, as we start to apply that stress, strain can build up. Now, strain can overcome the rock in one of typically three ways. The rock can actually fold or flow. And so folding and flowing here, we're referring to that as ductile deformation, or the other option is brittle deformation by fracturing. Now, the differences are typically how fast the strain is accumulated and how strong the rock is. So when we look at how things will deform, we have what's called elastic deformation. Now, if we consider this yardstick, if I bend it, again, it is deforming, but it is elastic. And so if I let it go, it springs back, and most of the time it will stay roughly its original shape. But if I bend it hard enough, it might snap. And so if that happens, I have exceeded its elastic limit. And because it snaps, it would do it brittly. On the other hand, if I bend it and then clamp it down and then leave it like that for, say, several months or even years, and then take the clamps off and it's held that bent shape, it has also exceeded its elastic limit, but it did it ductily. So again, when we exceed the elastic limit, we can do that either brittly or ductily. So with brittle, it breaks. Ductile, it either folds or even flows. Okay, so some factors that go into how specific rocks can deform. First off, well, what rock are we talking about? Is it something that's more rigid, or is it something that is softer and is more likely to fold, like these sedimentary rocks that we see here? Some other factors in addition to what rock type, there's the temperature. So higher temperatures can help to soften up the rocks, make them more likely to deform ductily, like by folding or flowing. There's confining pressure. Again, we already mentioned rock type, and then there's time. And so if we apply the same amount of force, very suddenly we might get the rock to fracture. If we apply the same amount of force but very slowly and gradually, it might be more likely to slowly deform, even though the same amount of force was applied. We just did it more slowly. Okay, now looking at geologic structures, sometimes it's helpful to kind of get the big picture because sometimes, again, we might see portions of this in a photograph like this, but sometimes we cannot get the whole structure in a single photograph. Sometimes you might have to take photography from further away, such as satellite imagery or aerial photographs. We may have to map out the whole site in order to see what the big picture looks like. So if we have some folds of one orientation in one spot and we see some other folds, again, if we can see a whole bunch of folds together, we can see more than if we're just looking at just a small portion of one of them. So here we're looking at a block diagram showing some of these structures. Now, whenever we see folds, we should automatically think that the crust has been compressed laterally. And again, this is what we see when we have rocks at a convergent plate boundary. But what we're looking at here on the map view is that, say this sandstone here that's dipping that way at 30 degrees, that's that there. And then over here, it's dipping towards the right at 85 degrees, so it's showing that there. And then there, it's dipping the other way again at 40 degrees. So the map view, we're adding in some additional symbols like this here and here and here to show which way things are dipping down, and we call those strike and dip symbols. Now, when we're looking at geologic structures, we're looking at how the folds or how other deformations have changed the shape of the rock. And so here we see some great examples of some folded rocks. Again, these are originally mostly horizontal, but then over here towards the left, they're now dipping towards that direction. Now, when we talk about the strike is an imaginary horizontal line on a bed of rock. And so we record that angle relative to north so we can plot it on a map. And then the dip is what direction things are dipping down. So this is actually probably what's more important. So we can see that again, these rocks over towards the right are somewhat flat-ish, but then over on the left, they are again dipping rather strongly towards the left of this image. And so here we see again one of those strike and dip symbols. Now remember again, strike is an imaginary horizontal line on the bed of rock, and the dip is what direction and angle it is dipping down below horizontal. And so this one is making a 30-degree angle. And so we write 30 degrees next to the strike and dip symbol to show which way things are dipping. Okay, so rocks won't always be dipping evenly in the same direction. You will have some folds involved, as we see here. Now, a fold is a bend in the rock. Now, this is again always due to compressive forces, which are shortening the crust and making it thicker. And so if we had the same rock flattened out, let's change color there for emphasis, it would be much longer. And so the crust has been shortened horizontally, but thickened vertically. All right, so when we have a fold, we name the folds based on how the sides, which we also call the limb of the fold, whether the limbs are above the axis or the hinge line, which is kind of the middle. And so the axial plane is just dividing that evenly in half. Axis is also referred to as the hinge. So an arch-shaped fold, again, the axis, the middle of the hinge is above the limbs. And so you can remember arch for anticline, and so that is that type of fold. Now, in the past, these were really important for the oil industry because a lot of oil tended to wind up in anticlines. So here's another example of an anticline. And so you can see this fold there. Let's get a color that contrasts just a little better. So you can see that arch-shaped fold there, and you can see in the background lots of other folded and really messed up rocks. Now a trough-shaped fold like this here is referred to as a syncline. Now synclines were generally not interesting to the oil industry because synclines tended not to have oil in it. All right, so here's another example of a syncline. So you can see that bed of rock that's folded like that. The axis is kind of like that, and so there's our axis. And then the two sides, this is a limb, and then here's another limb. So folds, again, we have the anticlines and synclines. Additionally, these can be themselves kind of lopsided or plunging down in one direction. And so they can be very even, if so we call those symmetrical, or lopsided asymmetrical. And so here on top we see an example of a fairly symmetrical flat line. Again, the axis of the anticline is fairly flat. Whereas on the bottom, here the axis is plunging itself. And so as this tends to erode, we tend to get these elaborate loops in these eroded plunging anticlines and synclines. Now here we're seeing exactly that in the satellite photos of kind of central Pennsylvania. So we can see all these loops that these eroding anticlines and synclines make. Again, these are plunging anticlines and synclines. Now they are forming these hills that are still forested because, again, they were not as easy to farm, so they cleared the low-lying valleys but left these exposed ridges in forest. So here we see on the left a fairly symmetrical anticline, and then it starts to get more lopsided in the middle. And by the time we get to this right one, we have one that has an overturned limb. And so that overturned limb, technically it's upside down. And so again, what's right was up as bottom, and bottom is up now. And then some other folds, we have what's called a monocline. And so monoclines are often kind of just simple stair-step folds like that. They are believed to be sedimentary rocks that are draped over a reverse fault in more brittle, harder, igneous, or metamorphic rocks underneath. And so there's the basic rundown of that. And here's an analog example. And so this is, I'm told, near the epicenter. So this is actually the fault trace from, should be that Chengdu earthquake back 12 years ago or so. And so basically that is where the fault was breaching the surface. This is a reverse fault. And so basically the rubberized surface of this running track just kind of draped over the fault scarp. And again, that's kind of our analog for one of these monoclines. Now a dome, you can think of that as a anticline that's just plunging on both ends. So it's really tightly packed like that. Now as a dome erodes, you'll tend to get, again, the oldest rocks exposed in the very center there, kind of forming a bullseye pattern. And then all the surrounding rocks are dipping away from the center. Now a basin is just the opposite. So in the middle, you get the very youngest rocks exposed, and all the surrounding rocks are dipping towards the center. And so you can think of this as a syncline that is plunging inward on both ends. Okay, and now here we're looking at a fault. Again, actually a series of faults. Now these are normal faults. We'll just go ahead and trace those faults in like this. Now, the reason why I love this particular example is because this is an almost perfect microcosm for Utah Valley. And so there's a block in the middle that is TIMP. We'll just put TIMP up there. So that's Mount Timpanogos. And then over on the left, we have Utah Valley. We'll just put UV there. And on the back side, this is where we have Heber and Midway, that area there. Now these faults in this example are normal faults. And so again, a normal fault is when the hanging wall is dropping down relative to the footwall side. Now a fault is just a fracture in the rock where there is a displacement of one side in relation to the other side. Now here we have a strike slip fault. And so in this example, this is a left lateral movement. I believe this may be one down in, I'm not sure if this is the one in New Zealand or not, but we know that this is not the San Andreas because the movement is the wrong direction. On the San Andreas, it's, they're moving like that. They're moving the opposite direction. And so this is a left lateral movement, not a right lateral. So not the San Andreas, but it's the same type of fault. Okay, now as far as any cracks or fractures in the rock that do not have any displacement on them, again, we can just call them cracks, fractures, or joints. Now, oftentimes you'll see that there's a whole bunch of these running mostly parallel with each other because they're caused by the same tectonic forces acting on a rock on a regional scale. And so these joints are the most common rock structure. And again, it's a fracture with no movement and usually parallel, and again, everything that we mentioned there. But these joints can govern the flow of fluids, whether we're talking about groundwater or some of the stuff that economic geologists get more excited about, like, well, oil and various mineral deposits can be governed and concentrated along some of these joints. And so here's an image that we did look at previously. Again, this is the Devil's Garden area near Arches National Park. Again, we have these parallel running joints. But as we mentioned, these joints can also enable the placement of large amounts of some ores. And so here we have a couple of really nice veins of gold. And well, I can tell you right off, I did not take this picture because if I ever found a gold vein like that, well, I'd be retired on some nice tropical island somewhere instead. Okay, so now looking at mountain belts and mountain building. And so here we have an image of the Matterhorn in Switzerland. So technically along the Swiss-Italian border. Yes, it is the inspiration for the ride at Disneyland. But it is a great example of, again, the byproducts of mountain building, an active mountain building right now. Now, the process of mountain building in geology we refer to as orogenesis. So orogenesis is mountain building, and an orogeny is a region of, well, mountains that are being uplifted during a specific time frame. And so all the orogeny, all this orogenesis includes all the folding, faulting, especially reverse and thrust faults, also metamorphism from some of the rocks that do not get uplifted. And so again, remember we have lateral compression acting on the crust. So yes, some rocks will be pushed up, others will be pushed down to areas where there's more intense heat and pressure that may enable metamorphism. We may also have some igneous activity going on, and so these types of mountain building can overlap volcanic arcs. And so those are a few things that we see. Okay, so as far as examples of mountain building, a great example, of course, is the Himalayas, the tallest mountains on Earth. But if you kind of follow the Himalayas westward, you go through the Hindu Kush of the Afghanistan region, the Zagros Mountains in Iran, the Anatolian Highlands in Turkey, and then over to the Alps. And so we have a somewhat continuous chain of mountains from the Alps to the Himalayas, where we have different continents that are converging on the southern border of Eurasia. The Himalayas are the furthest along. Others are, well, quite a bit behind it as far as the stages of development. But here, this satellite photo, that should be the Himalayas there. We have the Ganges Plain there. And then on the right, we have the Tibetan Plateau. Okay, so looking at different types of mountain building, we have lots of mountain building going on all around the Pacific Ocean. Over in the Americas, we have what's referred to as the American Cordillera, which most geologists lump in all the mountains from Alaska all the way down to Cape Horn in South America. And so this includes all the Andes and the Rocky Mountains and everything in between, because even though we're looking at two continents, they are currently semi-conjoined, but both moving westward, and we have mountain building going on at the same time on the western shores of both of these continents. So here we're looking at the major mountain belts in the world. And so here this is labeled the North American Cordillera, just looking at the North American part, but we can lump the Andes in with that as well. Again, all the mountains around the Western Pacific. And of course, then we have the Himalayas over to the Alps. But then we have some older mountain belts, like the Tasman Belt in Australia, the Ural Mountains in Russia, and then the Appalachians, the Caledonian Highlands, and the Atlas Mountains on either side of the Atlantic. Now, looking at the Ural Mountains specifically, again, this is an old mountain range that is still around. It does still form some highlands, but it is not actively being uplifted in any significant amount currently. And so this is also the stage that the Appalachians are in, or Appalachians, depending on your accent. Now, as far as the Urals and the Appalachians go, again, yeah, there's some decent topography in there, but most of us Westerners, particularly anybody from the Western United States looking at the Appalachians, most Westerners would just say, oh, those are just hills, not mountains. Now, the trick is the Appalachians formed long ago as, again, compressive forces applying on convergent plate boundaries as Pangaea was being assembled. But that was over 250 million years ago, and a lot of erosion has gone on since. And so I typically refer to the Appalachians as the pitiful eroded stumps of what used to be a truly great mountain range. The Appalachians formed as continents were colliding. They could have rivaled what the Himalayas are today, but a lot of erosion has gone on since then, and so we're not seeing mountains on the same scale. Again, if the Appalachians are hills by our Western standards, If we look at the Himalayas compared to the Rockies, again, the Himalayas are just mountains on an entirely different scale. And so the Appalachians to the Rockies are what the Rockies are to the Himalayas. Now, before plate tectonics, we had some other ideas about how mountain building occurred, which in hindsight look really silly. But the point is everything as far as mountain building and then geology as a whole just makes a lot more sense in the context of plate tectonics. Plate tectonics can kind of be thought of as the unifying theory for all of modern geology. Now, as far as how some of the basic ways that mountain building fits in with plate tectonics, of course, first and foremost, it happens at convergent plate boundaries, particularly near active subduction zones, but also where we do have some collisions going on in the case of the Himalayas. But if we look at the western margins of North and South America, as well as all around the Pacific, we see these volcanic arcs paralleling these subduction zones, and then some other mountain building that goes on with that. So here's an example of that. So we have, in both of these cases, some subducting oceanic crust. We have a volcanic arc that is developing there. Now the difference is on the bottom, this has gone on a little further. And so maybe we're advancing from, say, something like the Aleutians here to something more like Japan on the bottom. Now, looking along the edges of continents, we have what is referred to as the Andean type mountain building. And so, of course, this is typified by the Andes and the Cascades, where you have subduction offshore, but then you get big mountains, including many volcanoes, paralleling that. And so again, this happens along the margins of continents, again, wherever you have a subduction zone offshore. Now, with the Andean type mountain building, it is not just the volcanic arc. You can get a parallel mountain range developing that is the top of the accretionary wedge. The accretionary wedge is all of the sediment and other material that builds up in the subduction zone because of, again, erosion off of the land, washing that sediment in, as well as any sediment from the ocean that's been being scraped off, essentially, building up in that subduction zone, or on top of it rather, until in some cases it can be pushed up above sea level and becoming maybe a chain of islands or a mountain range running parallel to the volcanic arc. So just by way of review, with Andean type mountain building, we have the subduction going on offshore. Because of compressive forces, we get deformation kicking in, and so we'll get lots of folding and faulting and maybe some metamorphism happening. And that will lead to also the volcanic arc on the overriding plate. And so that is some of the things that we see on that leading edge of the continent. Now, a great example of this Andean type mountain building are the Cascades. And again, we have a volcanic arc like what we see with in Oregon and Washington State. There's Mount Hood in Oregon. And again, the volcanic arc develops on the overriding plate, which in this case is on the continent side. Now, in addition to the volcanism on the surface, you will have lots of metamorphism underground because of all that intruding magma, and that will cause some contact metamorphism. Now, running parallel to that, remember we have that accretionary wedge. So that accretionary wedge that is seaward of the volcanic arc, so it might be right along the coastline, or it may form a chain of islands just off the coast. but the accretionary wedge will have lots of folding, faulting, and everything will be just kind of really messed up. And then quite a bit of it may be metamorphosed. Now, a great example of this we have, of course, in the Pacific Northwest with the Cascades there. That is the active portion of the volcanic arc. And then running parallel to that, we have the Coast Range. Now, the Coast Range also goes down into Southern California, and that is running parallel to the Sierras, which are the former portion of that volcanic arc. So the Sierras were a volcanic arc, or is a former volcanic arc that was active before the plate boundary shifted to the San Andreas. Actually, going a little too far up there because that is the Berry area right there, and so the San Andreas is kind of like that. And so when the plate boundary shifted to the San Andreas, the Sierras mostly shut down as a volcanic arc, but other uplift has brought them higher and has exposed a lot of the granites and other intrusive plutonic rocks that were parts of the magma chambers of the volcanic arc that was once there. Now, of course, where we have mountain building at convergent boundaries, remember that if we have any subduction, again, it's the oceanic crust that is denser, and so that's the one that's being pushed down. But in the case of the Himalayas, it is still a convergent plate boundary. You have India going in there, but all of the oceanic crust in between has already been used up. And so now as India is colliding with mainland Asia, again, India is too buoyant to subduct down, and so it is going down a little bit, but is springing back up and causing the rest of the mountain building to kind of go into overdrive. Now, the collision is still going on today. It's been going on for tens of millions of years, but there's some new research that shows that the middle of the Indian Ocean plate, so the Indian Australian plate, is starting to buckle, form a new plate boundary. And so we'll see what will happen in a few more million years as this process completes. Will India just kind of suture on, and will the mountain building for the Himalayas fizzle out at that point? Now, as far as how things go, again, the Himalayas, they probably reached pretty much their maximum elevation. Yes, they're still being uplifted, but that uplift is mostly just keeping pace with the rate of erosion today. And so they cannot really get much higher than what they already are. But what has happened is that the area being uplifted has steadily increased. And so 40 million years ago is just this area here roughly that had been uplifted, and then it's just steadily increased over time. And there was 30 million years ago, and then 20 million years it expanded that far. And today, we'll just skip ahead, today it's encompassed that area there. And so the area being uplifted is expanding because the mountains can't really be pushed up any higher or much higher than what they already are. Now, again, this is kind of the situation that the Appalachians were in about 250 to 300 million years ago, as North America, Europe, and North Africa collided during the assembly of Pangaea. Now, again, this was a continental collision similar to what we have with the Himalayas, and so at the time, the Appalachians could have rivaled the Himalayas. And we see remnants of lots of activity there, including all the subduction, other igneous activity, and all the other fun stuff we see with mountain building. Now, if we look at the west, we see a little bit of a different story. Now all these different shaded in parts here, these are parts of North America that did not start off as part of North America. At least stuff that has been added in the last 100 million years or so. And so we refer to these as accreted terrains. And so you can see that title up there. We just have different crustal blocks that have been added onto or accreted over time. Basically, all the different shaded colors were different crustal fragments, island groups, sections of oceanic crust that didn't subduct properly or whatever else. They got plastered onto the leading edge of North America and just been slowly tacked onto it. And so in the past, as a student, I described this in a paper as roadkill tectonics. And so basically imagine all of that stuff as roadkill stuck on the front bumper of North America as it continues to head westward and has basically run over everything in its path. Now, in the geologic past, we're talking about, again, roughly 100 million years ago, there were offshore volcanic arcs on our side of what is now the Pacific, just like we see in the Western Pacific with Japan and the Philippines, except they're not separate islands anymore because we ran them over. And so they're tectonic roadkill. Now, rewinding back to the story of the Appalachians, we see the same thing happened again and again and again. And so if we look at the story back around 800 million to 1.3 billion years ago, there's already an old mountain range that had formed there from an earlier collision. And then between about 570 to 800 million years ago, it broke apart, so it started to rift apart. And so this rifting created a new ocean basin that we refer to as the Iapetus Ocean, so it preceded the Atlantic. And then after that had opened up and then it started to subduct away somewhere else, we had our side that was subducting underneath an island arc. And so this is similar to what has happened with Australia, because if we just change the titles here, if Australia is here, then this is Indonesia. It's the Australian plate that's subducting underneath Indonesia. But the problem is this thick continental crust cannot subduct. And so when that runs into the subduction zone, the volcanic arc gets plastered onto the edge of the continent. And so there we have that subduction going ahead, and then it collides. And then we have another volcanic arc doing the same thing. And then after that collision started, then we have North Africa coming in. And so when this collides, then, well, the mountain building goes into overdrive and we get the Appalachians proper. And so there we have the Appalachians starting to form as Pangaea is formed. And then things kind of fizzle out and then eventually they rift apart later. And so there we have the collision stopping, things starting to rest. And then a few million years later, things start to get stretched out the other way. Now with the accreted terrains, again, whether we're looking at the stuff that happened before the Appalachians or the stuff that happened along the rim of the Pacific, again, this is all adding on to the edge of the continent. So the continents have been growing over time as different island groups, fragments of oceanic crust. We refer to these as ophiolites. Not important for the test though. But island groups, seamounts, fragments of different crystal types, oceanic sediment, just everything that doesn't subduct properly gets plastered onto the leading edge of the overriding plate, and that resulting landmass just steadily grows over time. Now, as this happens, again, anytime we have any compressive forces, we start to form some folds and then eventually some faults. And so here, this fold has kind of been pushed as far as it can in this case, and then it forms what we call a thrust fault. So remember, the thrust faults, we have lots of overlap of the same beds. And so here's some cross sections of the border area between Idaho, Utah, and Wyoming. And so while we had collisions going on along what was then the coast, all this area further inland was getting compressed and resulting in all these stacked thrust sheets that we see across what is referred to as the overthrust belt. Again, the Utah, Wyoming, Idaho border region. And so here's that some of these thrust sheets as the leading edges of them have gone nearly vertical. This is the Bear Lake area, again along the Idaho-Utah border. And further inland still, we start to get some monoclines. And again, this is where we have brittle deformation, so some reverse faults in some of the more brittle granites and other igneous and some metamorphic rocks underneath. But then the softer sedimentary rocks, they just kind of fold over the top of that. And so looking at some other things again, here in this area, Colorado Plateau going up into Wyoming, this is where we have a lot of those monoclines. Across much of the rest of this area, we had these thrust sheets. But now this region here, what we call the Basin and Range, this area is now being stretched out as these old thrust sheets have been chopped up by normal faults. And so with those normal faults, that Basin and Range region is now being extended. So it's being stretched out. Now there's a bit of debate among geologists about what the driving force behind this is. There's at least a half dozen competing hypotheses, each with their own merits. In actuality, it may be a combination of factors rather than just one factor on its own. Okay, now part of this could be in part tied to what we call isostatic adjustment. And so basically, if you have some denser rock or dense material that is still lighter than the stuff underneath, it will float a little lower. And if it's less dense, it'll float a little higher. However, well, if we look at not just the density of the material floating, but how much material, if we pile on more stuff, even though it's less dense, some of the lower stack is going to start to sink down in response to that. And so this adjustment is referred to as isostasy, or we call it also isostatic adjustment. So if you imagine you have several blocks of wood floating on water, again, the water is modeling the mantle in this case. So remember that even though the mantle is mostly solid, again, it is denser than the material above it, denser than the crust. And so the crust is essentially floating on top of the mantle. But if we take one of these blocks, and again, this thicker block, you have the same proportion, the same percentage of that block floating above as you do for some of the thinner blocks. But because it's a bigger block, there's just more of it above. So these would be our mountains. But if, let's say, we shave like an inch off of the top of that block, the rest of it would spring up. And so again, these are isostatic adjustments. So we get some vertical movements that may be involved in lots of things we see across the edges of the plates and their interiors as well. This is especially true for areas that were glaciated during the Ice Age. And so here in this little animation, we have a glacier developing, and as that happens, the crust sinks down. Then as the glacier melts, the crust springs back up. But it's kind of like those commercials you may see later at night for those memory foam mattresses that as you know, in the, you always have a demonstration where they're pressing their hand down on it, then they take their hand off and it slowly springs back up. So that is just like the isostatic adjustment for the crust. It does spring back up, but it does so slowly. And so we still have some uplift of areas that were glaciated even thousands of years after the glaciers melted away. Okay, so some mountain building in areas away from plate margins. This includes, well, the Rocky Mountains and Utah. Now remember that the Basin Range, again, that is everything from pretty much the Wasatch over to the foothills of the Sierra Nevadas. But remember that this area is experiencing extension, not the compression we usually associate with mountain building. Meanwhile, right next to it, we have the Colorado Plateau that is higher than what you would expect it to be for that far into the interior of the continent. So there's several factors that could be at play here. Could be some differences in the flow of the mantle. And so there's maybe some additional upwelling underneath the Colorado Plateau or the Basin Range. So nothing quite on the scale of a mantle plume, but maybe some extra buoyant mantle that is helping that to be pushed up. There's also several other competing theories that involve really shallow subduction of some former plates during that time of accretion. There's plenty of evidence for that. The problem is there is, again, about a half dozen different theories for this that all have their own merits, but it's probably a combination of factors. And so again, this upwelling that may be causing the extension of the Basin Range that started about 50 million years ago and is still going on today. And so we don't all agree on what the cause of it is. What we do know is that if the extension continues, you can only stretch it so far before there's a new ocean basin in between, because you've thinned out the crust too much. But if we look at the evolution of the continents, again, we look at how, again, things have accreted and grown over time, but also new ocean basins opened up somewhere else. And we have just this continuing game of tectonic bumper cars around the world that would just see different land masses in different stages of the same thing. So this is the end of the lecture for structural geology and mountain building. So you should go ahead and do the homework for chapter 9.